Hello, welcome to the seventh homework of the machine learning. In this homework, we are doing key means clustering, and in this exercise, we will implement in the key means algorithm and use it for image comparison. And we're starting with a sample data set will help you gain an intuition of how the key means algorithm works. After that, you will use the key means algorithm for image compression by reducing the number of colors that occur in image to only those are the common in that image. I have to check it. Yeah, okay, it's working. Okay, in the first of all, we are implementing find the closest centroids. We have exercise one and computing centroid means we have exercise two, sample datasets, random initialization, and image compression with key means. To prevent errors, okay, you know this one. Okay, let me run the num first of all. Okay. One, implementing the key means. The key means algorithm is mentioned to automatically cluster similar data points together. Correctly, you're given data set X first sample to mth centers, and you want to group the data into fewer choices. I mean, the clusters. The key means is iterative procedure that starts by guessing initial centuries and then refine this guess by repeatedly assigning examples to their closest centuries and then recomputing the centuries based on the assignment. In the pseudocode, key means algorithm is follows. Okay, centuries we have x to k and iteration in all range. Cluster assignment step assign each data point to centroid. IDX correspond to the index of the centroid and assign to the example I. IDX flows constant centroid x and centroids. Move centroid steps compute the means based on centroid the assignment. Centroids compute centroids x IDX, which is this one. So IDX they can find closest centuries, x and centuries. We have x in here, and we have x and centuries and k. Okay, the inner loop of algorithm repeatedly carries out two steps: assigning each training example x to its closest centroid and recomputing the mean of each centroid using the points assigned to it. The key means algorithm will always converge to some final set of means for the centroids. However, the convergent solution may not always be ideal and depends on the initial setting of the centroids. Therefore, in practice, the key means algorithm is usually run a few times with different random initializations. One way to choose between these different solutions from different random initializing is to choose the one with the lowest cost function, the distortion, and one way to choose between these different solutions from different random initializing to choose. Okay, I'm sorry. You will implement the two phases of the key means algorithm separately in the next section. You will first of find closest centroid and compute centroid. Okay, first of all, we are finding the closest centroids. In the cluster assignment phase of the key means algorithm, the algorithm assigns every training example to its closest centroid, giving current position of the centroid. Okay, we are find closest centroids, and this is our function basically. So to read it, if you have to read it, this function takes the data matrix X and the location of all centroids inside centroids. It should output a one-dimensional array, a IDX, which is a number of assignment X. So IDX equal the length of the IDX is equal to the X, which is our element number. And hold the index of closest centroid evaluate a to k minus 1, where k is the total number of centroids. To every training example, the index range k to k minus 1, 0 to k minus 1, where I slide from what is shown in the lectures. Want to carry because Python list indicators. Let's say, okay, yeah, it's starting with the zero, special for every example, like we said. Where Ci is index of centroid that closest to Xi correspond to IDX, the eth element in the starter code, and Uj is the position of the eth centroid stored in centroids in the starter code. Because this is more. And I before I read this, I was understanding, but after I read it, I can understand. It's the L2 minus norm. If you get stuck, you can hint. Okay. Let me try it. Computer centroid membership for every example. Raise X and array M input values centroid and the array key and centroids IDX array like M centroids. Okay. I want to see the function also. And okay, first of all, it has a inner loop. So for okay, we have each element. We are using each element. So for E in sorry for E in range exit shape. Oh, I cannot write now. For every element which is the X shape, we are using it and must be set with zero. Mm, yes. Sorry. And minimize, yeah, okay, we are taking the square root and taking square root of it for other stuff. So I have to calculate distance. Yeah, I have to calculate distance and MP logarithm dot. Yeah, I have to use X and I'm taking the every index of it. I send roids. Usually equal the centroids because it's also in here anyway. Centuries, did I forget anything? I want to check a little bit this one. Yeah. Shape zero. Okay, we have here. Oh, okay. It didn't give me a whole code. For I in range centuries dot shape. Norm I X. It's not giving me norm IGA and not giving me the IDX code. Let me check it. IDX and pay argmin. Oh, okay, norm IGA. What? Why I cannot open? Okay, okay. Linear algorithm calculated norm. Okay, I calculated norm and IDX and distance. Okay. So where I was it hundred access one. Did I made some mistakes I guess. Yeah, I made a mistake in here. And yeah, okay. I have to calculate IDX I guess. So for each element equivalent okay that's what was it? Argmin. Okay. Argmin I don't know the argument, so I just want to check it. Arg AX is none, out none. Oh, okay. And I have to give distance in here. I guess it's okay. Let me run it. I'm not sure about it, but let's run it. And let's run this one. Okay, the code block prints the first 5 elements in the variable x and dimension of the variable. Okay, and okay, it's passed out, so it's true. And compute the centroid means given assignment of the every point to centroids. The second phase of algorithm recompute. So for each centroid, the mean of the points that were assigned to it. To reduce the error, let's completely compute centroids below the recompute for each compute. And we CK set of examples that we assign centroid k. Say, okay, set k. Constantly, if the example says x or n are saying centroid key equal to, you should update this one, and okay, if it's stuck, yep. I just write this code because I couldn't be sure, and I just go and check for the hints after I write this first one. So I will just run this one, and let me run this one, and in here k equal to centuries, compute the centuries in here actually we are computing to compute the idx over here, and we are assigned to xk to equal idx, which is the difference points for all values to the centroids, and we are calculating the mean of it. So actually, we basically are computing the or centroid. And yes, we are given the k true, and this is our centroids. Compute centroids. And this is true. Okay. Key means on a sample data set. After complete the function, and yeah, we are just basically working on the k-mean works. I will run this one, which is giving codes. Yep. After our iterations, we are you can see the how it changed, and random initializing the initial assignment of centers for the example dataset we designed so that you will see the same figures in figure 1 in practice. A good strategy for initializing the center is to select random examples from the train set. And K means again, but this time random initializing center is the run cell low several times and observe how different clusters are created based on the initial point chosen. This is our chosen. Did anything change? Yeah, as we can see, till we run it, or iteration numbers are changing, but they're probably run it before, and it's just iterating itself. Yeah, because number 4, number three again, and number 4, it's just going random. And image compression with the key means and original this one, and let me run this once. Um, in straightforward 24-bit color representing of a image, Each pixel is represent a three 8-bit unsigned integers, and that's specifically the red, green, and blue intensity values. This encoding is often referred as the RGB encoding. Our image contains thousands of colors, and in this part of exercise, you will reduce the numbers of colors to 16 colors. As we can see, we're just using show pilot to visualization it, and compressing the image. Special hardware selected. Yeah, actually, basically compression image. Yeah, this is our original image, and run key means you need to first transform the matrix original image to dimension matrix, and we have means on the pixels. I'm just first running this one because it's kind of same as we did it before. Yeah, this is the most used 16 colors, and compression we're just choosing and putting them into here, and our images changed, now has less information, but we have more space to use it, and this is much more bigger than. Thanks for the listening. Have a good day.